It is time for some science. So thank you all for coming out and adapting to this, the new reality of COVID demo shows here. This is actually the middle of the Atlanta Science Festival. It started last Saturday. There are, I think, 97 different events happening across the 2 weeks. And so there are several more events happening in the next week. So if you are looking for some more things to do, then there are definitely some opportunities for you. But today we want to present several different demos for you. And we are from Emory University. I am Dr. Doug Mulford. And I love the fact that I get paid to do this and come out and blow things up for you. So that's kind of fun. But we have several students here from ChEmory, which is our undergraduate chemistry club, and PAX, which is our graduate chemistry club. And a lot of what we do in these clubs is outreach with science. And so we are so glad to be able to be here with you today and share some of our favorite demos. As I mentioned, we are also trying to broadcast this on 88.3 FM, so you might be able to hear it in your car there, but you know, it might be just live there. Also, we may have to adapt a couple of these demos as we go because it's windier today than we were expecting. So of utmost importance is safety. So I need to make sure my demonstrators are safe. But we're going to start today with something called the Co2 Rainbow. And so we want to do a demonstration for you. Now, there's a very large glass tube there. And it's filled with this really fancy chemical called dihydrogen monoxide. It has a couple other names like hydroxy acid or water. Is what you might know it as. So we have just some regular water in the tube there, and we're going to add to this something called Fisher Universal Indicator. Now this is a mixture of several different chemical compounds, and it changes color based on the pH. Ooh, what's pH? Now pH is how acidic, like vinegar it is, or how basic, like soap it is. So this particular compound, the more towards the blue and the purple, the more like soap it is, the more basic it is. The more towards yellow and red, the more acidic it is, more like vinegar or stomach acid. So right now you should see that that's green. That's good, that's our tap water, and that is neutral. That's coming out at pH of 7. Now your body actually maintains a pH of around 7.35 to 7.45, so that's close to where our body is. So we want neutral things. Alkaline water, really bad for you. Don't try to do that. Your body will just get rid of it. All right, now we're going to add to this some sodium phosphate tribasic. What is that? If you want the chemicals, it's PO4 3-, but it comes from phosphoric acid, which is actually what they put in Coca-Cola and 7-Up to give it that little bit of a tang to it. So it's a really weak acid, and this is just, we've removed the protons, but you can see that we got a nice purple color. So that means that our pH has become basic. It's become more like a soap. All right? So what we really wanted to show you with this demonstration, something about carbon dioxide. Now you're breathing. This is where you participate. Everybody take a breath. Okay, you all did some science there because your body breathed in oxygen and you breathed out carbon dioxide. So what we're going to do is we have some solid carbon dioxide. You may know this as dry ice. It is at 79 degrees below 0 Celsius, and we're going to add it to our tube here. Now carbon dioxide just has carbon and 2 oxygens. There's no protons, which is what you normally need for an acid, but this one's kind of cool. So we've got some bubbling. Yay, science that bubbles is always a good way to start. But watch the color as it goes. And so, we've gone from purple. What's purple? We've gone from purple to a kind of a green color, maybe a little blue. Now, you are welcome to say ooh, ah, and oh to any science that you think is cool. Or you can honk your horn if you're in your car. But there we go. All right, we've gotten to green. So we've gone from a base down to neutral. And I'm seeing, is there a little yellowish to it? A little bit. So it's definitely acting as an acid. And this is really important for us in the environment. When we talk about acid rain, we talk about the acidification of our waterways. That is coming from carbon dioxide. So here we're showing that carbon dioxide actually acts as an acid, which is what causes those problems for our environment. We have to be careful with it. Okay? We got a little drip coming out there, but we definitely have gotten to yellow, so we've gotten down to about pH 5. So we'll let that just kind of boil for a while we do some other demos for you, but there is the carbon dioxide rainbow for you. Okay? All right. So chemists are interested in how different materials will react with each other. Like we saw there, the carbon dioxide, the fact that it's an acid. But we are also interested in what effect temperature has on different materials. So what we've got here is another demonstration for you where we're going to work with liquid nitrogen, and I'm actually going to hand the microphone over.
All right, hello, my name is Courtney.
And I'm Landy.
Technical difficulty. All right, thanks. So what we have in here is liquid nitrogen. Nitrogen is what's in our atmosphere, what's all around us and what we breathe. And our atmosphere is 78% nitrogen, 21% oxygen, and the remaining 1% is a mix of other gases. So to start off, I'm going to put in a racquetball. Would you mind giving this a little bounce? All right, normal racquetball going in. And we also have a banana, a normal banana that you eat. And I'm going to put this in the liquid nitrogen. So the liquid nitrogen is really, really cold. It's about -320 degrees Fahrenheit. So the reason it's so cold, or the reason it's liquid, is because when the molecules get much colder, they can become liquid as opposed to the nitrogen that's in the air. It's gas, it's a lot warmer, so the molecules are moving around a lot quicker. So the racquetball and banana are going to take a little bit to freeze, and now I'm going to put in, the balloon. Do you want to blow up the balloon, Landy? So while she's blowing that up, I'm going to put in this flour. So the flour is not going to take too long because it has a lot of water in it, which freezes really quickly. So I'm going to stick this in for a few seconds, and we're going to see what happens. All right, just about done. All right, see how beautiful it is? Are you ready? It shattered! Because it was so cold. All right, so now Landy's going to stick in the balloon. And give that a little bit of time to freeze. Okay, so in the meantime, we are going to take out the racquetball. I think we're going to need some gloves for this. All right, so now I'm going to bounce it. What do you think is going to happen? All right, ready? All right, now I'm going to take out the banana. It's frozen. It'll break your teeth. All right, now I'm going to use the banana that's normally kind of mushy to hammer this nail into the wood. And now for the balloon. It's a poodle! Some magic happened with the liquid nitrogen. Thank you.
All right, so when we get things cold, their properties change quite a bit. And we have, this is special liquid nitrogen that's been to college. That's why it can make that into a poodle. All right, next thing we'd like to do for you, whoops, is, okay, we're going to do a demonstration for you called the grain elevator. And we want to look at a combustion reaction. Now, combustion means burning. And from a chemistry point of view, that means combining something with oxygen is what happens in a combustion reaction. So what we have in this jar up here, I'm going to grab your jar, is something called lycopodium powder. Now, this color may look a little familiar to you. You've seen it. In fact, I see it on that red color right there, and I see some there. This is pollen. We actually paid somebody to collect pine tree pollen for us. So this is a jar of just pure pine tree pollen. And you can do that, please. Yeah. So we're going to try some on this little dish here, and we're going to see if we can get it to burn. So again, burning is reacting with oxygen. And so see what we got here. We got our magic fire stick, lighter, and nothing. It's not working. And the problem is that the powder can't mix with the oxygen of the air to do the reaction. So instead, Carla's going to put this into a tube here that has a funnel on it. And when she blows through the funnel, it's going to spread the lycopodium powder out. And that's going to make it be able to react with the oxygen better. So let's go ahead and see this. All right, we're going to need a countdown here. So if we can get a horn countdown in 3, 2, 1, go! Fireball! Woo! We need to do that again, don't we? We got to do it one more time. Yeah, we got to do it one more time. So let's try one more. This is really... Try turning this down. Okay, we're closer than we thought we were going to be. All right, so she's loading it up again. Now, this is important for us to know that almost any material that's finely divided enough will become flammable. And so we have to be careful with that. So let's go ahead and do this again. All right, in 3, 2, 1, go! All right. There was actually a sugar plant in Augusta, Georgia about 10 years ago that exploded because of this reaction. We call it the grain elevator because you have to be careful in the Midwest if you're welding on a grain elevator. It's actually better to weld on it when it's full, because when it's empty it can be filled with the corn dust and then this reaction can occur, which is a problem. All right, so from the combustion reactions, we're going to go to start talking about some polymers and long chains. Okay, so I'm going to hand the microphone over again.
All right. So what we have right here is some sodium alginate. Sodium alginate is a polysaccharide polymer that's found in the cell wall of algae, that kind of green, gooey stuff you see around water sometimes. So a polymer is a bunch of molecules stringed together in a chain. So if you think about a bunch of people holding hands, each person is a molecule, and together they make a polymer. So the sodium alginate has our polymer, and sodium has a +1 charge, which is attracted to one side of the polymer. So when we put it in the calcium chloride, the calcium has a +2 charge and actually will link together two polymers, kind of like this. So we're gonna put our sodium alginate in our calcium chloride, and it's gonna cross-link our polymers, and it's gonna make some gummy worms. And you can actually pick them up. They're really slimy. All right, thank you so much.
Actually, you raised a really important point. You said eat it. Well, we have to be a little careful now. Actually, that reaction that we just did there is one you can do at home, because you can order sodium alginate and calcium chloride online, and it would actually be safe to eat. We're not going to do that because I have no idea what else has been in that beaker. And so we have to be careful with that. So we don't eat anything that comes out of our lab, but really, cooking is just chemistry for hungry people. So it's great. So we like to do that. So from gummy worms to gummy bears, we're going to talk about this.
Hello, hello. So now this time we've got the screaming gummy bear, right? For the screaming gummy bear, we're going to use two different things, potassium chloride and gummy bears. So we don't actually need all of what's in these two things to make our reaction, right? You saw me blow the fireball earlier, right? This is a different kind of combustion reaction. And for this one, out of these two things, we need two separate molecules, glucose and oxygen. So our potassium chloride has three different elements: potassium, which is found in bananas, chloride, which is found in salt, and oxygen, which we breathe in. You take a deep breath in. There you go, you got some oxygen for you. And now gummy bears, they've got an important sugar called glucose, which is what our body uses to give us energy. And so what's really reacting, like I said, is our glucose and our oxygen. This combustion reaction is actually called cellular respiration. It's what happens when we're breathing in air and it's combining with the food that we eat to give us energy and lets us move around, jump around. That's why the kids have a lot of energy, right, kids? Woo! And so what's happening right now, she's heating up the potassium chlorate, which is going to break it down to give us the oxygen that we need. And what we're about to do, now that it's all melted, we're about to drop our gummy bear and it's going to scream. Make that combustion reaction, it's going to light up. You might even get to see the purple light that it gives off. You guys ready? We've got our gummy bear. Our screaming gummy bear. And that's what's going on inside your body. Don't eat gummy bears, kid. That's too much sugar for you.
All right, luckily the reaction goes a little slower inside our bodies, but yeah, so if you eat a bunch of gummy bears, this is why you have so much energy. You're getting that reaction. And we can see the flames still going on. My goodness, that gummy bear had a lot of energy. Now, another way we measure that energy is calories, right? Calorie is a measure of how much energy you can get out of the food. All right, from bears, we want to move to a slightly different animal. Looks a lot similar. Oh, okay, maybe not. We want to talk about some elephants. All right, so what we're going to do today is a demonstration for you that some of you may have seen before, because this is one of the favorite of science demonstrators. This is called elephant's toothpaste. Now, into this jar, she is pouring hydrogen peroxide, H2O2. Now, you may have used this before because you can buy it at the drugstore. It's often used for disinfecting wounds and things like that. And you may have noticed it always comes in a brown bottle. And it comes in a brown bottle because hydrogen peroxide can break down into water and oxygen gas. And light actually makes that reaction go faster. So they put it in a brown bottle and to kind of slow that down a little bit. Now, you can buy 3% hydrogen peroxide at the drugstore. And then as a consumer, you actually also have access to 10% hydrogen peroxide. That's what's used in bleaching hair. Okay, it's really strong. It can cause burns. So that's the most that you can get. They think we're trained scientists, and we can actually get 30% hydrogen peroxide. So what we just added here was 30% hydrogen peroxide. Now the reaction will still go, but the problem is I'm not seeing a lot of bubbles there because the reaction is actually slow. It will take us a couple of months. So we're going to see if we can speed it up a little bit, and we're going to add something called a catalyst. A catalyst is just something that makes a chemical reaction occur faster. This particular one is potassium chloride. Sodium chloride is the table salt you all have at home. So instead of sodium, we just move down one on the periodic table to potassium. And so we're going to see what happens when we add our potassium chloride to this. All right, here we go. Mix it together. Whoa! Oh my gosh, there it goes. There it goes. It looks so jiggly in the wind. So we moved it, so we did. Okay, whatever. So I don't know, somebody did that once and decided that that's what an elephant's toothpaste would look like. So that's what we call that one. You can find on the internet people who have done this on ridiculous scales. Mark Lobler holds the world record. I think he used 2,000 liters of hydrogen peroxide, and it was so much. He had an apparatus that weighed a ton, and it actually launched it in the air. So it's kind of, I'm not going that far. So I love the internet because there's always crazy people out there who will do things. All right, so what we've got now is, this is me. All right, balloons. Okay, sorry. All right, I get to do a demo for you today. I've actually spent time over the last couple of weeks training all of the students in the science and also safety, because safety is very important. So right now, if you talk, or like I'm talking, you have a muscle in your body called a larynx. The larynx vibrates, and as it vibrates, it collides with the air molecules that are in your throat and causes them to vibrate. Those vibrations move through the air, and that makes the sound waves that we hear. All right, so what I want to do, though, is instead of having regular air inside my larynx, I want to change it to a different gas. So to give you an idea of what we're going to do, air normally has a molecular weight of about 28. So just number itself doesn't matter, but it's about 28. I want to replace that with helium. So I have a helium balloon here. Helium has a weight of only 4. So at room temperature, the helium molecules are moving much faster than are the air molecules. As a result, the speed of sound is faster, and so when my larynx vibrates, it's going to be able to move faster through that. So we're going to see what happens when we do that. All right, so let's take our balloon here. Whew. Let's see if I can do this without cutting myself. Okay, so what I'm going to do is I'm going to breathe in this gas, and I'm going to keep talking in a tone just like this. And we're going to see what happens if we change the speed of the molecules that are in my larynx. Did it work? Oh, yes, it worked. Okay, now when I talk, things sound a little bit different. Because the molecules are moving faster, the pitch goes up, and I sound like a munchkin. Okay, and so the speed of sound is much faster, so when the vibrations occur, they move more quickly, and the pitch goes up because the peaks of the sound waves are closer together. Okay, is that better? Okay, I'm back to normal. All right, so thank you so much. All right, now as a chemist, I get access to some things that you don't normally, and one of them is this, a balloon. Okay, you actually get a balloon, but what's in the balloon is a little different. So this time, my balloon is not lighter than air helium, it's actually heavier than air. This is something called sulfur hexafluoride, or SF6. Now it has, instead of being 4 or 28, it's about 120 for its weight. So it's much heavier, so that means that these molecules at room temperature are moving slower. So we're going to see what happens when I put that into my voice box here. Once again, I will talk the same way. You know what, we're just doing it this way. Don't tell my dentist. Okay.
Okay, and now when I talk, my voice sounds a little bit different because the particles are moving much, much slower, and as a result, the pitch goes down. Luke, I am your father. I just have to do it that way. Okay, so
I'm trying to get it out of my lungs. Is it going to work? Okay, yay! I'm not passing out. All right, it's the one demo we don't let students do for that reason. Because it pulls in low places. But so that's what happens a little bit with the speed of our molecules. All right. So we've got another demonstration now. I've got a few more for you here. This one is called burning money. And sorry, I've got a balloon. Don't use your teeth to pop a balloon. Okay, so we're going to work with a little bit of money here, and we're going to see what we can do with our money. And so Landy is setting something up here. She's got some corks just for some insulation. I did say it was burning money. And we're going to fill this tray. Now this tray is like a standard lasagna tray. It is a casserole dish that is something called borosilicate glass. You may know it as Pyrex. And it can withstand temperature changes. She's now pouring into that some alcohol. Now this is 70% isopropyl alcohol. It's very similar to ethanol, but it's mixed. It's 70% alcohol and 30% water. And that water is going to be very important for us in a moment. So what we're going to do is she's going to get that in there, and then we're going to take the extra and put it back because safety is important. All right, we got a $1 bill, legal tender in all 50 states. We're going to put it into the alcohol. And then let's see if we can get this thing going. Do you have your magic fire stick? Okay, let's try that. All right. We're going to see what happens when we do our oxidation reaction. Remember, that means we're setting it on fire. Is it going? Oh, come on, get going. All right, where is it? Where's the big toy? All else fails, get the blowtorch. Good? Is it lit? Oh, there it's going. It's going. So it's a little hard to see because ethyl alcohol or an isopropyl alcohol burn very cleanly. But you may start to see some flame here. Okay? So if you look down here, the wind is causing havoc here. But you can kind of see some flames coming up here. I can feel the heat. All right, so what's going to happen is we've got a dollar bill in there. She's going to pick up that dollar bill, and we're going to see what happens. Watch the dollar bill carefully. It is on fire. Oh, we're burning money. It's like paying tuition. And it survived. The dollar actually survived the fire. So we're going to do it one more time for you here. Okay? And you can see that it is actually on fire, but even though it's on fire, fire's out, and the dollar bill survived. So what's going on here is, well, we singed a little corner there, but the water that's in there actually absorbs the heat. And so the paper can never get too hot. It never gets up to 451 degrees Fahrenheit, or Fahrenheit 451. That's the temperature when paper will spontaneously burn. And so the water absorbs the heat instead of the paper, and it survives. Okay. All right, so let's go ahead and move this to the left. We have 2 more demos that we want to do today. Okay, so we can take our time and enjoy this one because we're going a little ahead of schedule. That's okay. So in this bottle, we have mixed together some iron oxide. Now, iron oxide, Fe2O3. You guys, sorry to come in here. You all have seen iron oxide before. Oh, we melted this. Okay. All right, I need to deal with this. Give me the fire extinguisher. Thank you. This is why we always travel with one of these. Melted our lid. Okay, science! All right, there we go. See, this is the joy of live science. Okay, all right, so let's talk about this demo again. Wow, I made a mess. Okay, all right. Actually, this makes a point that it's very important, and we enjoy doing these demos, but we do talk about safety, and we do talk about how to do it, and we are prepared in case something goes wrong. Or something goes different, shall we say. Okay, all right, so what we have here is we have thermite. This is iron oxide. Now, iron oxide is just actually rust. So we have really, really pure rust. And we've mixed that with aluminum metal, very finely powdered aluminum foil. And it turns out, once you mix the two of those together, it's very stable at room temperature. She can pour it out, she can shake it up, she can hit it, nothing's going to happen. But it is also considered a Class 1 incendiary device, and it's illegal to take this across state lines. Because once this reaction goes, it's pretty impressive, as we will see in just a moment. So we're going to do something called a redox reaction. We're going to have electrons move from one compound to another. And so we're going to go from iron oxide to iron metal. So I want to describe to you what you're going to see here. They're putting a piece of a magnesium metal in there. That magnesium is going to be our fuse. We're going to light that. You're going to see a really bright white color. And actually, you've seen that before, because that's the white color in fireworks. So we essentially have a little bit of a firework that we're using to start this. That's going to burn down, and it's going to start the thermite reaction. Now, thermite has been used for a couple hundred years because they welded railroad ties with it. We'll see why. Because when this reaction starts, we're going to go from room temperature to 3,000 degrees in less than a second. You will see sparks coming out the top. I agree. You're going to see sparks coming out the top, and then watch the bottom of the flower pot, because that iron, 3,000 degrees, it melts at 2,800. So it's going to make molten iron, and that molten iron is going to pour out the bottom of the flower pot. So let's go ahead and set this thing on fire. All right, we see the bright white light. Keep watching. There's this reaction starting. All right, watch the bottom. Right about. Come on, you can do it. There it is. There's the 3,000 degree molten iron pouring out the bottom there. Okay? So it is toasty here. We can't touch that for about half an hour, but we can show you. We did this earlier today. So we just made this. Now, this isn't too useful for us today, but if you have a couple of railroad tracks and you do that over the gap between the railroad tracks, you actually end up welding them together, which is what this reaction's been used for historically quite a bit. Okay. And we got one more for you. If you guys have the thermal gloves, can you slide that back? Thank you. some olfactory chemistry here. That thing smells horrible. But yeah. Okay, so we're going back to our liquid nitrogen for you. And what we want to do is we want to look at liquid nitrogen and we want to interact it with hot water. So to remind you, liquid nitrogen is the air you breathe, but it's made so cold that it condenses into a liquid, 300 degrees below 0 Celsius. We're going to that one's Fahrenheit, sorry, 200 below 0 Celsius. And then we're going to add to that some boiling water, which is at 200 degrees Fahrenheit. So we're going to have a 500 degree temperature change. Now they're pouring the liquid nitrogen in right now. All right, I'm going to watch to see how much we got. Let's get some more. Oh, enjoy, pour it in. Now you're seeing a little bit of a cloud forming because it's actually causing liquid water from the air to condense into water droplets. Okay, that's probably good. And those water droplets reflect the light. It's hard for me to say. And bounce it around. And so a cloud, when you see a cloud, it's actually liquid water droplets. So what we're going to do, though, is we're going to add some ping pong balls to it just for fun, because, you know, why not? So we got those in there. And then we're going to pour in 4 liters of boiling hot water. Or we're going to try. It takes a little bit of practice here. We're going to see what happens when we combine these together. Now we have our blue minion bucket, because every mad scientist needs their minions. All right, so let's do one more countdown here. In 3, 2, 1, go! Whoa! Science! And we have a cloud and a wet demonstrator. All right. So thank you all so much for coming out today. We had a lot of fun doing demos for you. Hopefully you enjoy science.